Good evening, Nitya. Good evening, Gayatri. Good evening. Vanessa, shall we start? Okay. I request all of you to join. Okay. I request all of you to kindly mute your microphones throughout the session. Good evening, all. Myself, Minnie Thomas, Head of the Department of Mathematics, Marthoma College, Tiruvalla. I welcome you all to the second day of our international online workshop, Initiation into Linear Algebra. Today, we have with us Dr. Gayatri Verma. She has done her PhD from NIT Calicut. Her research work introduced and developed the theory of multi-Poisson sets that can handle ill-posed problems with multi-level uncertainty. Currently, she is pursuing her postdoctoral work in matrix analysis at Indian Statistical Institute, Delhi. Her research interests include theory of multi-fuzzy rufflets, Hadamard's powers of positive matrices and simplicity. Ready. Gayatri, we are really proud of you. May you fly high in life and success be with you also. On behalf of the organizing committee and all the participants, I extend a warm welcome to Dr. Gayatri Verma. Our principal, Dr. Varghese Matthew sir, is also with us. We welcome you, sir. We have Dr. Ajesh K. Sakariya of Chemistry Department with us. We welcome you, sir, and at the same time, we are extremely thankful to you for helping us out with the live streaming. I also take this opportunity to welcome all the participants. So, let's start our today's session on operators, matrices, and eigenvalues. Over to Gayatri.
Thank you, ma'am. Thank you for the introduction. Good evening, everyone. So, I'm happy to be a part of this lecture series. Am I audible? If someone can confirm.
Yes, ma'am.
Yes. Okay. Thank you. So, yeah, as I said, I'm happy to be a part of this mini lecture series. So, let me just start my presentation. Just a minute. Give me a second. There is a slight technical issue. I'll just start the presentation in a minute or two. Okay?
Okay.
Is the presentation visible now?
Yes, ma'am. Screen is visible, ma'am.
Okay. Thank you. Okay. So, let me start my lecture today. Okay, so the title of my talk is Operators, Matrices and Eigenvalues. So I have a small disclaimer to make. So most of this, so the presentation very much is taken from there is very resemblance from the linear algebra and Wright by Sheldon Axler textbook. So it's mainly because of two reasons. One is it's such a good book to start with. For a beginner, it's a very good book. And we want to actually you all to get familiarized with this book. At least we all wanted that you should know there is such a book, and you can start with linear algebra from this book, and then later on you can try other textbooks. So that's why mainly I have stick on to this textbook. Okay. Now, so a few words about the lecture series itself. Different. What is our aim? You have seen yesterday from the lecture 1, it is fundamentals of linear algebra. Srinod sir has done a very great job in introducing many, all the basics in a very short span of time. And today I'll be speaking on the operators, matrices, and eigenvalues. And this is, see, you can see that interdependence kind of thing. So how one lecture is needed for or as a prerequisite for the coming lectures. And here you can see lecture 3 and lecture 5. These lecture 3 and lecture 5 are somewhat, and then lecture 6, of course, is a main goal or kind of thing we can say of this lecture series. So all the other things will be very supplementing to these these 2 lectures, that is 3 and 5. And 6, the lecture 6, you can see that it's a, as the title itself suggests, that it's a beauty of linear algebra which we want to convey through that lecture, which will make use of all these factors, all the lectures, but you can actually listen to that very independently also. As far as I have heard that it's very self-contained. So I just wanted to give a whole lecture series in a nutshell, that's all. Okay, and how all these things are interdependent. Okay, so then I'll come to the aim of my lecture, or the lecture 2. So I will show the equivalence of linear maps and matrices. So initial part will be focused on that. And then I'll prove the existence of eigenvalues for operators with finite dimensional vector spaces over C. And then an upper triangularization of operators on finite dimensional vector spaces over C. And a brief introduction to inner product spaces and orthonormal vectors. So a small word of caution here. If you are a beginner, in the linear algebra, you don't have to worry about any of these things. You may or may not understand everything from the class. It may depend, but if at all you don't understand everything from the class, it is okay. It is completely fine. All these materials will be provided, and the video will be available in the YouTube. So, and the textbooks and all those things are available. So materials are there. So if you give some time, you can actually work on it. Okay. Now, okay. So this is the my lecture. Hello. Hello. Okay. I hope somebody else's mic is on. Okay. So brief introduction to inner product. This is the main. Okay. Let's recall. Let's start the lecture with recalling some. Hello. Okay. So we'll start with recalling some of the subjects or some of the topics which you have seen yesterday. So Shilsa has started with vector spaces and given a lot of examples, and in fact he has given very good examples, and some of you have tried also. We were very happy seeing that. And then he moved on to subspaces, and with the subspaces, how you can construct more subspaces using the direct sums, then the linear independence. So when I am saying all these things, or when you see this definition or these terms, just try to recall or just try to think about the definition of all those things in your mind. Okay. So you have seen linear independence and dependence, a spanning set. So I think yesterday he has mentioned spanning list. Okay. Basis, dimension of a vector space. Then linear maps, a lot of examples for linear maps. Then when you have a linear map, you can talk about null space, range, then rank nullity theorem. That was the main goal of the lecture 1. And then he stopped with the isomorphic vector spaces. So some of these things which I will also make use in my lecture. So that is, so the linear dependence lemma, which states that if you are given a linearly dependent list of vectors, okay, if you are given a linearly dependent list of vectors, one of the vectors is in the span of the previous ones, and furthermore we can throw out that vector. Like you can do without that vector also. So that is what it means. Okay, even though if it is not there, it is not going to make any change. You will get the span of the original list itself. Now, if you have any linearly independent list in a vector space, you can finally you can extend it to a basis of the vector space. And if you have any spanning list of a vector space, it can be actually reduced to its basis. Then, at the last, you have seen that a linear map is completely determined by its values on a basis. That is, you don't have to know the value of this linear map on all the vectors of the vector space. Just knowing its values on the basis elements itself is enough. So that we will see more or less today. So that is the same thing which I have written here also. If you have a basis, I have written explicitly with the, or more or less mathematically I have written here. If V1 etc. Vn is a basis of V, and T from V to W is linear, then the values of T V1 etc. T Vn determine the values of T on arbitrary vectors in V. Okay. So how does that math mean? How is actually that? How does that mean? That means you have a vector V, element of V, element of the vector space V. V, you know that by the definition of basis, there exists scalars C1, C2, etc. Cn, such that V is equal to C1, V1, etc. Cn, Vn, right? Then I can write. So what will be TV? TV will be is nothing but C1 TV1 plus etc. plus Cn TVn. Why? Because of the linearity of T. So which means for any V element of V, I actually get TV just by knowing TV1 etc. TVn. So that is the, I just stressed on that point. Okay. Now you see matrices. So matrices are, so I'll just show this definition. This is the one definition which you might have seen at the first. When you first encounter a matrix, this must be the definition you have seen, that it is a rectangular array of elements. An M by N matrix A is a rectangular array of elements of F. But now when you are like, you can actually here say something more about the matrices also. Or as you see the second sentence, matrices are used as an efficient method of recording the values of T vj's in terms of a basis of W. Okay, so we'll come to that point again. So what is basically these columns? That is what we are going to see. Basically, these columns are nothing but the coordinates which you have seen for. So TV1, if I am writing TV1, where is TV1? TV1 is in W, and W has got a basis, right? So say W1, W2, etc. Wm, we don't know. Yeah, so for that I am writing A11 W1 plus A21 W2 plus etc. plus A1M Wn. So this TV1 is an element of W, and hence it can be written as the linear combination of elements of its basis, and I have written that. And you can see that this is nothing but the first column of the matrix A. So in a similar way, I can actually generalize this to, like, that is how we are actually seeing the matrices here. So suppose T is an element of L of V W, and we have a basis for V, and then we have a basis, this V dash for W, and the matrix of T with respect to this basis is the M by N matrix. So here I have chosen this as the notation for the matrix of T with respect to the basis V and V dash. Okay, that is what this means. is equal to whose entries Aij are defined by this what I have written earlier. Okay, the same thing. So TV1, TV2, all those things. So here I have repeated the same thing again because I just want to make it clear or to stress this point. You to understand this point more. So that's where the jth column of this matrix is nothing but the scalars needed to write TVJ as a linear combination of W1, W2, etc. Wn. So what does this mean? This means for every linear map I can find. So here actually I have just written, there are entries here. I have just written the jth column only, okay? Just to get so there are points here, A11, A12, etc., A1J, etc., A1, okay, like that. So basically how it is, if I am writing, this is W1, W2, etc., Wm, and then here V1, V2, etc., Vn, I am writing V1 in terms of W1, W2, TV1, sorry, TV1 in terms of W1, W2, etc., Wm, TV2 in terms of like that, okay? Okay, so let's see one example. So some of the examples, metrics of a linear map. Many of you might have seen already, but let's just go through for the completion, logical completion. So let T element of L of F2, F3, where F2 you might have seen yesterday, F can be R or C. So dimension 2, and then T of xy is equal to, so this is the linear map given by T of xy is equal to x plus 3y, 2x plus 5y, 7x plus 9y. So what you have to check? First you have to look at the, so if no particular basis is mentioned, we usually take the standard basis. So here you can check for this 1, 0 and 0, 1. These are the basis, this is the basis in F2. And I will check for this T10, T01, and let's see how it is coming. So T10 is 1, 2, 7. You can check actually. Just putting all the Y0. Okay, 1, 2, 7. Okay. Now T01, what will be? 3, 5, 9. And now writing this in this column, you will get this as the matrix of T with respect to this basis. Okay. With respect to the standard basis in both sides. Okay. Now, the differentiation map. A little more. So where P3R is the set of all polynomials with degree at most 3 and P2R is with at most 2. So this is the standard basis 1x square x cube, and here this is 1x square, and this is the differentiation operator, right? Nx raised to n minus 1. So now you will check what is, so for example, I have to write one as d of, suppose I'm just taking this as d of x square, what it is? 2x. Now how I can write 2x in terms of 1x square? So 0 into, 1 plus 2 into x plus 0 into x square, right? So what will be the which column? 1x square. So x square column, that the column will be 0 to 0. So this will be the column. In a similar way, you try to find the matrix of this. I will give the answer. This is the matrix. So you just verify. Okay. Now let's see algebra of two matrices. Algebra. So if you already know how to add two matrices and scalar multiplication, everything you know. But let's see, I have just defined matrices, right? So when you go for the completion, I have to do in such a way that everything will follow. So the A plus B is this matrix, right? If you have two matrices, A plus B is nothing but the entry-wise sum. So this means any entry in the A plus B matrix is the entry-wise sum. Okay, A plus B, lambda A, and with addition and multiplication. And this is something which you can check with addition and scalar multiplication as defined above. This form a vector space of dimension mn. Please verify this. And then in a similar way, you can say that ST element of LVW, lambda element of. So this actually yesterday you might have seen that the set of all linear maps from V to W. So this actually you can see that the matrix of S with S plus T with respect to this basis is equal to this sum of individual matrices. So in a similar way you can see, actually you have to verify this. Okay, this is I'm just mentioning here, you have to convince yourself that both of these are actually together, fall in place. Okay. Now here also you can see that with addition and scalar multiplication defined as above, this also forms a vector space with dimension m. Now here I have defined sum of two matrices and the scalar multiplication of it. So you might have in your class you know already how to multiply two matrices, right? But if you look at the addition and scalar multiplication, it's quite natural, right? If you have two matrices, you just add the entry wise. And scalar multiplication is also just multiply each entry. But when it comes to multiplication, it is not quite natural. The process of multiplication which we are following, it's not quite natural, right? So, but here you can see one reason for that, why it is defined so. So that is the point which we are coming to. But so I hope that is not a question. So I am continuing. So let U, V, W be vector spaces with bases. Okay. With basis BU is equal to U1, U2, etc. UN, BV equal to V1, V2, etc. VN, and BW is equal to W1, W2, etc. WP respectively. Okay. So now consider the linear maps T from U to V and S from V to W. Thus, the matrix of S composition T is equal to the matrix of S multiplied with matrix of T. Okay, so now you might have got some idea, okay, why, so when is actually this composition of two linear maps is defined, so that is, we here see, you can see that T, S composition T is a linear map from U to W. Okay, so then why we always insist upon that M by N matrix should be multiplied with some N by P matrix, right? So here I think you are able to see what is that reason. So this is just one way of saying or seeing how natural the matrix multiplication is. There are actually other ways also that you, but this is one way. So to make sense of this matrix of the linear transformation of composition of two maps. Okay, so this is something which you have to verify. Please do it on yourself so as to get that essence. Okay, so till now what we have seen is, if you are given phi and where W are finite dimensional and if a basis has been chosen for each of these vector spaces, so that is one thing which you have to make clear in your mind, that this is, the matrix is something basis dependent. Okay, then for each T element of LVW we can talk about its matrix. Okay, okay, now so which means given a linear map I have a matrix. Whether given by a matrix say, whether we can talk its linear map. Okay, so way to do that is, you know how it is. We have seen that the linear map is completely determined by its values on the basis, right? So if also the T is from, like, if I'm defining from T from Fn to Fm, so actually you can yesterday Shinod sir has talked with this isomorphic between vector spaces, and in fact actually pin down that for a finite dimension, there exists in fact only one vector space and up to isomorphism. Okay, so in a similar way, you can find that if Fn and B is a vector space of dimension n, Fn and B are actually isomorphic, that you can see. So then if T is from Fn to Fm, then I define so you have a matrix A with the columns A1, A2, etc. A, M, right? Since it is an m by n matrix. So I am defining this TV1 as the vector A1. So this is a vector A1, okay? Then TV1 as A1, TV2 as A2, and like that. And then, etc. TV n is equal to AM. Then so then you have a linear map, right? Then I have defined the linear map on a basis, and you are done. So in such a way also you can see, and in a similar way actually I can say the same thing. It is actually the same thing, but if you want to see it as a linear map, I am just explicitly giving this map. That T is, I am defining T from Fn to Fm by T of x is equal to A into x. A is the matrix, given matrix A into x. And now you can check that this is actually a linear map and it will serve the purpose. Or it will serve that, what is if you have a matrix A and I am getting a linear map. So in effect, what do we have now? We have, if I have a linear map, I have a matrix, and I have a matrix, then I have a linear map. So it depends upon the situations which you want to work with. Okay. Sometimes it will be easy to work with matrices, sometimes it will be easy to work with maps. So that's how. Okay, now we'll just go to the concept of inverse of a linear map. So you know, so a linear map, so this is the definition. If a linear map T element of L of V, W is called invertible. If there exists a linear map S from W to V, such that ST equals the identity map on V and TS equals the identity map on W. And in other words, I can say that S is the inverse linear map S element of L of WV such that ST is equal to I and TS is equal to I is called an inverse of T. And of course, there exists only a unique inverse, and for an invertible linear map, it has a unique inverse and it is denoted by T inverse. So this is one theorem. So it actually, I mean, I'm not going to prove it. I hope you can assume it, or many of you might have already seen it. Okay. A linear map is invertible if and only if it is injective and surjective. So let's see some of the examples. So just keeping this theorem, keep in mind a linear map is invertible if and only if it is injective and surjective. Okay, zero map, whether it is invertible. It won't be. Why? Because it is not injective. For all Tx is equal to 0 for all x. So then it is not injective, not invertible. Then identity map, you can check that. Please verify that it is invertible. Now let's look at one non-trivial example. T from P of R to P. P of R is the set of all polynomials with real coefficients. And I am, you have seen actually this is one of the examples which was given in the first lecture. So that's why I have to take this. So T of P of X is equal to X square into P of X. Whatever be the polynomial I am taking, I am multiplying it with X square. Whether this map is invertible. So just think whether the linear map should be invertible if and only if it is injective or and surjective. So this won't be, because I hope you have given enough time. So just think this won't be invertible, and reason also you can see that whatever be, if in this range, whether constant maps will be there, like no constant maps will be there, no polynomials of with x only, 2x, 3x, nothing will be there, because whatever be, we are getting x square into that. So it is not surjective. So this is just one example, as one is not in the range. Okay, if you don't get at least one, then you can. Now the backward shift linear operator. So that means backward shift linear operator is So if I have T of x1, x2, etc., this is the sequence set of the sequences. Okay, if infinity also you have seen yesterday. So then this is x2, x3, etc. Okay. So just think whether this will be invertible. No, it won't be, because 1 0 0, not only 1 0 0, I have just given one example. You can see that whatever comes in this will be mapped to 0 0 0. So the null space won't be singleton set 0, the null space won't be the 0 space, it will contain some more. So then again it is not invertible. I hope you remember that if T is invertible, if I have a linear operator from T from V to V, and I am restricting that to the first subspace U1. So T restricted to U1, from U1 to, I don't know actually whether it will be T restricted to U1 will be an operator, right? If it is an operator, okay, if T restricted to U1 is actually mapping U1 to U1, okay, suppose. So that is actually we have seen in the first two cases also. So similarly, I am trying to extend it to M subspaces. You will get see what is going to happen. Okay. Now, in a similar way, so if I am going to write this, the basis of this operator in this extended basis, you can see that. Just erase the initial things. Okay, just a minute. Okay, I'll stop with this, I think. Okay, so if I am writing this, so all these things I am, sorry, okay, T restricted to Uj is from Uj to Uj. If this holds for each j, okay, you can say I'll write it. Well, if this happens, I'm not saying that T restricted to Uj will be an operator to operator, but if this is happening, then what can be said about the matrix of this operator as a whole from T from V to V? So that you can see here. Okay, so the matrix of V is something which I have extended from each U1, U2, etc. UN, right? So here you have U1, so here you have U2. So I have, by this I mean that the basis of U1, U2, etc. UN, and similarly here U1, etc. UN. Okay, so what is meant by this? T restricted to Uj maps Uj to Uj only. So which means if I write any element, if this the first basis, right? U1, U2, say suppose U1, U2, etc. UK. Here there are k elements, but T restricted to UK. So T restricted to U1. So T of U1 will be an element of this U1 only. Then U2 again will be not U2. The basis again here, okay, that will be again, so one element here. So I don't want the elements of U2 to write the basis elements of this one, okay. So this will actually restrict here, but only non-zero elements will be coming here, and whatever be coming here, that will be, so here from here it is U2. No, like so I suppose I'll write some U1 element of U1. Okay, I think I'm making a lot of chaos here, but still u1 element of u1, t1, u1 is an element of u1. So I don't need any element from u2 to write. So all those coordinates will be 0 only. Okay, that is what I am meaning from here. So u1, u1 here. And then if I am writing about u2, then I just need only this much. Okay, so u2 will be coming only in this part. u2 writing in terms of u2. Then u3 coming with writing in terms of u3 here. So this means only non-zero parts will be coming in these areas. All the other areas, it will be 0. See? Now if I have, so here I have actually taken many restrictions, right? I have mentioned that if t restricted to uj is from uj to uj, if it is like that, then if all these things happens, then only I am writing, I can get this kind of a structure for the operator. So that matters. So that matters, and then if there exists such kind of subspaces, if there exists such kind of subspaces, what can we call them? And if they have, then what is the, I'm sorry, I have taken some time here, just going quickly through that. So the same thing I have mentioned here, I'm just writing properly, okay? So take any v element of v. So now I am starting with any vector space. So it has a v element of v with non-zero vector, and I am taking a subspace, that is u is equal to lambda v, span of v the set of all scalar multiples of v. Then u is a one-dimensional subspace of v, right? Because only one, it is a span of v. Then every one-dimensional subspace of v is of this form for a non-zero v, that you can see later. You can verify that. So in general, let v is equal to u1 direct sum, etc. direct sum u1, where each uj is a proper subspace of v. Okay, suppose v is like that. And to understand the behavior of t, that is what you have seen earlier. And to understand the behavior of t, we need only understand the behavior of each t restricted to uj. Why? Because it is easier to deal with the smaller subspaces, right? Rather than working on the whole vector space. So then, yeah, that is what I have written here. And so whether we can do that. But then what is one problem arising there? Then t restricted to uj need not be an operator. It need not be mapping uj to uj. So then I will consider it in such a way that, okay, only decompositions of v of the form above where t maps uj into itself. If I am considering like that, then what can we say about that kind of subspaces? So how does t look like if t restricted to uj is an operator? So that is what I have just shown you. That is this is something which you can actually, you should convince yourself. Say u1, so here the basis of u1, here the basis of u2, like that. And here also, since it is a basis, sorry, it is an operator, I will be taking both same basis, right? Like that, okay? So here you have to see this. How does t look like if t restricted to uj is an operator? That is what I have earlier also. So here there will be zeros. So this, seeing this, you can guess that this is a matrix with a lot of zeros, right? Which makes it easy to work with the. So these kind of subspaces should be named a particular way. So that is not, they are known as invariant subspaces. So suppose t element of L of v, a subspace u of v is called invariant under t if u element of u implies tu element of u. In other words, u is invariant under t. So this is basically a subspace is said to be invariant under t if t restricted to u is an operator on u. Okay. So these are some of the examples. Just verify it. Okay. 0, v, the null space of t, range of t. Okay. Now we come to the definition of eigenvalues. So eigenvalue is coming from the same thing which we have just mentioned, like t element of L of v. A number lambda element of f is called an eigenvalue of t if there exists v element of v such that v not equal to 0. That is something very important. A non-zero vector, if there exists a non-zero vector v such that tv is equal to lambda v, then that lambda is called eigenvalue of t. And of course, what comes along with that eigenvector? So v is called the eigenvector. Okay, so now just try to say what or prove or convince yourself this T has a one-dimensional invariant subspace if and only if it has an eigenvalue. That is actually more or less what we have seen or discussed earlier, but you can try to say it again. Okay. So now you have seen the definition of eigenvalues and eigenvectors. So eigenvector is a vector, a non-zero non-zero vector v element of v is called an eigenvector of t corresponding to lambda if t v is equal to lambda. Now these are some of the equivalent conditions to be an eigenvalue. So you know how I defined eigenvalue. If tv is, if there exists a non-zero eigenvector, so the non-zero vector v such that tv is equal to lambda v not equal to 0, which means t v minus lambda v is equal to 0. And this I can write in terms of because of the linearity, I can write it like this, right? So what does this mean? V is not equal to 0, right? So this is an operator and t minus lambda v is equal to 0 for a non-zero vector v, which means this is not injective. And that actually in a finite dimensional vector space, we have seen one theorem earlier that one thing implies the other. Injectivity implies surjectivity, but here not injectivity actually we can say about not surjective. And that can imply t minus lambda is not invertible. So now just pause for a minute and you can, for a second, and you can see some similarity with what you have seen already, the definition of eigenvalue from the matrices in terms of matrices. Okay. Now, what is the behavior of the eigenvectors with respect to the distinct eigenvalues of a t? So this is something very easy. You can see that first. So if you have a distinct eigenvalues lambda 1, lambda 2, etc., lambda m, and their corresponding eigenvectors v1, v2, etc., vm, then v1, v2, etc., vm is linearly independent. That is what we are going to prove. But I'll just go quickly through the proof because everything is there in the slide. So first, this is by proof by contradiction. So first, we suppose that it is linearly dependent. So if it is dependent, then recalled in the first slide that there is a linear dependence lemma, which says that there exists one element in that set which can be written as the linear combination of the previous vectors. So let k be the smallest positive integer such that vk. So let vk be the first vector which can be written as the linear combination of its previous vectors. Okay, then there exists, so which means linear combination, I can write it as linear combination vk equal to a1 v1 plus etc plus ak minus 1 vk minus 1. Okay, now I apply t to both sides of this equation. So what does this become? tvk means tvk. What is tvk? We have taken such a, it is a eigenvector, so it will become lambda k vk. And here also it will become a1 lambda 1 v1 etc vk minus 1. And to the same equation, to this equation number 1 itself, I am multiplying lambda k on both sides. Okay, here lambda k on both sides, and then I am, so here you know what you can see, these two became same, like lambda k vk and lambda k vk, and now I subtract, so that you can see here both sides of the equation number 1 by lambda k, and then subtract the equation. Okay, so this was the first equation. Actually, I have to write lambda k vk a1 lambda k v1 like that. This is not the equation number 3. This is again the equation number 1 itself. So there is no typo here. Pardon me. Okay, then subtract the equation 2. Then you will get like this. Okay, this will be the equation you are getting. Now v1, v2, etc. vk minus 1 are linearly independent, which means vk was the first one to be depending on the previous vectors. So till now, till vk minus 1, it was linearly independent. So which means these scalars, a1 into lambda k minus lambda 1, lambda k, all these scalars should be equal to 0. But these quantities cannot be 0 because we have taken eigenvalues distinct. And none of the previous eigenvalues were same with the lambda k minus 1. So none of these become zeros, which means AIs should be 0. All AIs are 0. So that is the same thing which I have mentioned. The equation above implies that all the A's are 0. However, this means that Vk equals 0. Vk equals 0. Vk, what was Vk? Vk was an eigenvector, so then it should not be a 0 vector. So that is a contradiction, and hence we got the proof. Okay, now you have seen that if there are distinct eigenvalues, then the corresponding eigenvectors are linearly independent. Now, this is something from that you can, if you have a linear independent set, you can extend it to the basis. Now, how much we can get? At most, we can get dimension of V distinct eigenvalues. So that is something for a operator we can have at most dimension of V distinct eigenvalues. That is very clear. Okay. Now from here you have seen that if we have an operator, it can have at most dimension V distinct eigenvalues. But let us see whether an operator may have one. It doesn't guarantee that it has one. If at all it has one, then it must be at most distinct dimension of V. Okay. Okay, let us look one example. So this is T element of L of R2 defined by T of x y is equal to minus yx. This is nothing but a counterclockwise rotation by 90 degree about the origin. So that is like this. So if I have a vector like this, and then I am sending that to under this linear map, sending to 90 degree rotation. Okay, counterclockwise rotation. So I'm considering this as a perpendicular. Okay. So whatever be the vector here will be sent to like this with 90 degree rotation. So if an operator has an eigenvalue, so I'm going back to the definition, an operator has an eigenvalue if and only if there exists a non-zero vector in its domain that gets sent by the operator to a scalar multiple of itself. So if it is an eigenvalue, it should, like, if this vector, then it is TV equal to lambda v, it should be somewhere in this line itself, okay, if it has an eigenvalue. But this t is actually taking back to, it's taking a counterclockwise rotation. In that rotation, it will never happen, right? It will never send it to a linear or a scalar multiple of itself. So for this operator, what I can say, it doesn't, if at all it had a eigenvalue, it should have been like that, but it is not like that. So which means T has no eigenvalues. Now look at one another example, T element of L of C, and you can see that it is actually the same.
Hello, ma'am.
Thing.
Ma'am, sorry, ma'am. Could you please explain the example one more time?
The same example?
Yes, ma'am. Rotation.
Okay. Yeah.
Thank you.
See. So see here, what is this? Okay. Sorry for my bad drawing. Okay. So. So this is R2, right? If at all I have, so suppose I am just considering this is a vector in R2, okay? Under the linear map, T, the linear map is a counterclockwise rotation by 90 degree. So T, if this is xy, then I am sending that to this part, okay? T of xy, that is minus yx. So actually, not exactly here, but it should be somewhere here, okay? It's mainly because of my bad drawing, but yeah, which means it is just rotated 90 degree to this part, okay? So in that way, but if this operator T had an eigenvalue, then T of xy should be something like lambda into xy, okay? So, but here it doesn't happen, okay? It won't happen because then it should be somewhere here itself. T of xy should be also somewhere in this line, line. But you can see that it is not staying in this line. It will be going to this part. So that is why you can't say that. You can say that it has no eigenvalues. Okay. I hope now it is clear. Otherwise, just
Yes, ma'am. Yes, ma'am. It's clear.
Okay.
Thank you so much.
Okay, thank you for confirming. Okay, now suppose the same thing I am looking at in the complex vector space. So T of W z is equal to minus z W. Then just see, when I am just taking this vectors, I am taking vectors. In these vectors, you can see that T of 1 minus I is nothing but I into 1 minus I. So here you can see that T z is equal to some lambda z, right? And here also you can see that T of 1i is equal to minus I 1i. What does this mean? This means I and minus I are eigenvalues of T. So see, when I considered this map on R, L of R or R2, it doesn't have a eigenvalue. But when I came to complex vector space, it has eigenvalues. So what does this mean, or how can we say that? So there is one theorem which says that every operator on a finite dimensional non-zero complex vector space has an eigenvalue. So actually it just makes use of, just a minute. Okay, maybe I won't go to that. Okay, since it's time, I don't have time to go much deep into this. So, okay, every operator on a finite dimensional non-zero complex vector space has an eigenvalue. This actually makes use of the fundamental theorem of algebra. So we'll just quickly go through the proof. Suppose V is a complex vector space with dimension n greater than 0 and T element of L of V. Choose V element of V with V not equal to 0. And then see V, T square V, etc. So whatever we are starting from very basic steps, okay? V, T square V, etc. T raised to n into V. And here you can see how many of them are there. They are actually n plus 1 elements are there. So they cannot be linearly independent because we have taken the dimension of V as n and they are n plus 1 vectors. So they cannot be linearly independent. So then there exist complex numbers, A naught, etc., not all 0, such that A naught V. So here I just have to make one point. This T square V, T raised to n V are actually makes sense, so that we can say about the polynomial of operators and all. I'm not going deep into that. So that will make sense. So I think you will be able to assume that. So A0 V plus A1 TV, etc. This would. And then with the same complex, same complex numbers, coefficients, I'm taking a polynomial with P of z. Now for this polynomial, I have the fundamental theorem of algebra, right? And for that, I can have the factorization like this: C z minus lambda 1, etc. So that why? Because all these are coefficients are coming from C. Okay, that's what fundamental theorem of algebra says. And now I am just replacing all this and making this polynomial as a polynomial of operator A0 I plus etc. plus V. And then this I can write it as T minus lambda 1 I etc. T minus lambda m I. Okay, why? Because we have this factorization. And I have used that factorization here. And this is equal to 0, which means for at least one j, this should be equal to 0, right? And for that, T minus lambda j I is not injective, and which means lambda j is an eigenvalue. So now we have proved every operator on a finite dimensional non-zero complex vector space has an eigenvalue. So this something which we have is a good thing. Okay. So this is again matrix of an operator. I have already mentioned. You have seen also. I'm just mentioning that if we are taking a linear of an operator, then we will take both sides the same basis. And okay, then again the explanation of the same things. So here it will be square matrices rather than rectangular matrices. That's all. Okay, now we're coming to one another part of the main part of this, one another aim of my lecture, that is upper triangularization. So now we have seen VB a finite dimensional complex vector space and T element of L of V. Now from the theorem which we have just seen, I can clearly say that it has an eigenvalue, right? Say lambda. Now let V be the corresponding eigenvector. Again, so this is something which we recurrently use. Extend that to a basis V, basis of V. Okay. Then again, the same thing which I have mentioned earlier itself. So then the matrix of T with respect to this basis has the form this. So in this, by this star I mean all this part there can be non-zero elements. No, non-zero elements. Okay. So first column will be this. This is something which I am very much sure about. Okay. In a similar way, I can actually extend this. So I can similarly say, I have actually earlier also we have seen the same thing. So I don't have to. So in the next thing I can say that this is lambda 1, lambda 2 here, and all the other things will be 0 here. So in a way I can proceed, and that's what upper triangular matrix is. This is just a definition. You all are familiar with that, but I'll just state for the completion. It's called an upper triangular if all the entries below the diagonal equal to 0. Okay. Now this is one important part of conditions for upper triangular matrix. So when can we say that a matrix of T is an upper triangular, matrix of an operator is an upper triangular matrix? So these are some of the equivalent conditions, but most of them are very only we need to prove 2 implies 3. The other things are from the definition itself very clear. Just read one more. TVJ is an element of span of V1, V2, etc. Vj for each j equal to 1, 2, etc. n. Then span of V1, V2, etc. Vj is invariant under T for each j equal to 1, 2, etc. That is something we are going to prove. So suppose T holds. Okay. From 2 we know that, okay, the 2 holes means this is true for each j. That means TV1 is an element of span V1. TV2 or V2 is an element of span V1, V2. Similarly, you can go on. But what is that? What is span of V1 will be obviously contained in span of V1, V2, etc. Vj. And similarly, again, V1, V2 will be again contained in V1, V2, etc. Vj. And if this is the way, now if V is a, so what we have to prove? We have to prove that span of V1, V2, etc. Vj is invariant under T. So which means I am taking a V element of span of V1, etc. Vj. And then we have to prove that TV is again an element of the span. This same thing. That is by the definition of invariant. So if V is a linear combination of V1, V2, etc. Vj, what does that mean? There is actually nothing to prove. From that itself, it is very much clear. Like V is equal to some C1, V1 plus etc. plus V1, Vj. And from all these things, I can say that TV is element of span of V1, V2, etc. Vj. So, in other words, span of this one is invariant under T. So, actually, one thing which you have to very clear is this structure which we are getting from. So, first one is TV1 is an element of span of V1. So, you will be getting only this part. Then V1, V2. So, you will be getting only this part. Then you will be getting this. This is something which actually mentioned. So, basically, the crux of this theorem is nothing but you are actually writing this T in the matrix of T will be looking like this, and here it will be 0, and here there are non-zero parts. So this is actually what you are getting from this theorem. Okay, so since I have very little time left, I just have to go through quickly to everything. Okay, now you have seen that there what is an upper triangular matrix, and one very nice thing about now we can say that V is a finite dimensional complex vector space. So just notice that V is a finite dimensional complex vector space, okay, and T element of L of V. Then T has an upper triangular matrix with respect to some basis of V, okay, with respect to some basis of V. That is something which I am going to prove, but again I am not, I won't be spending much of the time because the little more has to be done, okay. So this is one good thing. Initially what we have seen, for any operator or for any linear map, I have a matrix. Now you are actually seeing that for any operator on a complex vector space, you are actually getting an upper triangular matrix, which is even better, right? Which is even better. So we have a basis. With respect to that basis, T will be an upper triangular matrix. So I'm restating it because you just to settle it in your head. So that's why. Okay, so the proof is again like it's a classroom kind of proof, but we'll just go through it. Proof is by induction on the dimension of V. So when dimension of V, everything is clear, I have already mentioned. Now suppose this desired result hold means there exists an upper triangular matrix whose for all vector spaces with dimension strictly less than dimension of V. Okay. Now lambda be any eigenvalue. Whether we can say that there exists an eigenvalue of T? Yeah, we can, because earlier we have seen, since we are talking in the complex vector space, the theorem which we have just seen actually guarantees you that there exists an eigenvalue of T. Now, if you have an eigenvalue, you can again start with all those things. I mean, you have vector, eigenvector, and all those things. So, if I have so lambda is an eigenvalue of T, and I am taking mu as equal to range of T minus lambda I. So, I need a subspace. So, this is a subspace. And what is the dimension of U? What T minus, the equivalent condition of being an eigenvalue says that T minus lambda I cannot be surjective. So, which means dimension of U is less than dimension of V. We will prove this U is invariant under T. Okay, this is just a calculation. This T. So what we have to prove? U is invariant for proving U is invariant under T. You have to prove, if I take a U element of U, TU is again in U. TU is again in the subspace U. So I have just wrote TU in such a way that T minus, this is just an algebraic manipulation, or otherwise also you can actually see, but it's okay. Just for the time being, let's see T minus lambda I U plus lambda U. Okay, this is nothing but TU itself. So, but what is this? T minus lambda I U will be again element of U, but why? Because U, the subspace U is nothing but the range of T minus lambda I. So that will be again element of U, and this is a scalar multiple of an element of U, and U is a subspace, so this also should be an element of U. So this means TU should be an element of U, which means U is invariant under T. Okay, here there is an under T, I have forgot to write. And this T restricted to U is an operator on U. Okay. T restricted to U is an operator on U. And what was the dimension of U? It is less than dimension of U. And by our induction hypothesis, what we can say, for this T restricted to U operator, this operator, I have an upper triangular matrix, or I have a basis corresponding to which, or with respect to which, the matrix of T restricted to U is an upper triangular matrix. And so now what is this? If I have a basis of a subspace, then I can extend it to the basis of the whole space, right? So that is something which I am going to do. So I extend that to a basis of V. That is 1, U1, U2, etc. Um, and V1, V2, etc. V. And again, for each V element of, or for Vk, all these Vk's, what is the element? That is what we are seeing. T Vk. Here you know already what is happening. T minus lambda, that will take that to itself. And here tvk is equal to t minus lambda into vk plus lambda vk. And the definition of U shows that t minus lambda I vk element of U. This is also again that algebraic manipulation. Okay. And why? Because this is again range of t minus lambda is U. Okay. And this is an element of span of U1, U2, etc. Un. And thus this equation above shows that tvk is an element of span of U1, U2, etc. U1, V1, V2, etc. Vk. And if I write in this, so actually you will get that this matrix will be matrix with respect to this basis will be an upper triangular matrix as we decide. Okay. So this, so the main aim of my lecture was 2-3 things that I have covered. Now, suppose, so yesterday you have seen that the vector spaces, whenever I was, so Shinod sir in fact actually started the motivation for vector spaces from R2 and C2 or like C and like that. Because these are the structures which we know from the beginning and then we actually generalized from there. Okay. Now if we have more structure in R2 or so what is actually in R2 we have actually a lot of freedom, or we can talk, in an earlier example also we have seen that we have taken we have sent this vector to a rotate, we rotated it right to a 90 degree and send it to there and all those things. But in general vector space I don't know whether that is possible, right? In a general vector space I don't know whether that is whether we can do, we haven't seen any such kind of things like an angle or a length of a vector, nothing yet we have seen. So if I am actually, so that are actually the properties which are in R2 and C. So if I am actually generalizing, can I continue? So I'll continue. Okay. Hello. Okay. Can you mute the participant or? Okay. Maybe I'm audible and can continue. Very less time left. I'll continue. Okay, R2 or C. There we can talk about angle, we can talk about the length of the vectors, and I'm trying just to extend that to a vector space also. Okay, if we have these kind of additional structures in our vector space, what can we say, or whether we will get more? So with the things available with us, whatever we in a complex vector space, I have got up to upper triangular matrix. Okay, that is very well good and fine. But if we have more structures in the vector space, whether we can talk more or whether we will get more nicer structures. That is actually the essence of the coming lectures maybe. Okay, so this is something which I am trying, just I have mentioned you earlier that vectors in R2 and R3, there we can talk about the length of this vector in R2, in R3, all these things you have seen somewhere in your earlier days, and defining. So from this, actually length of this vector and seeing this, whatever we are always doing from whatever we have available with us, and then we generalize it to a generalized setup. So here I am defining this is the notation for the length, and I am defining norm. Norm is actually the length of the vector, that's all, in such a way. And you have already seen in your classes that dot product, right? Dot product is you have two vectors, x and y element of Rn. Dot product is x1 into y1 plus etc. plus x and y. Now, if the dot product has some properties, these kind of properties, that is non-negativity and all those things. And we can say, so in a product, So I am going to generalize this to, so here this dot product and all those things were working in well in Rn, but I want to talk in general vector spaces. So there I am going to generalize this dot product as inner product. But then I have to actually include the complex case also. So I am actually borrowing this heading from Sheldon Axler, that's complex complication. So how can we deal with when complex numbers are also there? Okay, so just recall that this if I have a matrix, I have a complex number lambda is equal to a plus ib, then absolute value will be like this, conjugate will be this, and they have this relation. Now I am defining. I just want to define. So one property which you have seen here, maybe x dot x is greater than or equal to 0 or x. So one property which we have seen earlier, that inner product or the dot product x dot x should be x1 square plus etc plus xn square. So that actually we have to take care in the complex case also. So just give a thought why the absolute values were needed. Okay, this is a question for you. You just think why it is needed, and so this modulus actually suggests that. So this is something which we need. Okay, for then how should I? So this norm of z square should be z dot z also. Okay, this should be satisfied, and in such a way, how can I generalize the idea of dot product as inner product? And then that suggests that the inner product between two elements in Cn should be like this. And I'm going to the property or the generalization inner product. So inner product is actually a function, not a property. I'm sorry for that. So inner product is a function that takes an ordered by UV to a number inner product. This is the notation, inner product UV. This is an element in F. This is a scalar, just a scalar. So two vectors are sent to a scalar, and which has these properties, non-negativity, and if it is equal to 0, if and only if equal to 0, and this is linear, u plus v, inner product of u plus v comma w will be equal to uw plus vw, and the linear homogeneity, then conjugate symmetry, inner product uv is equal to inner product vu conjugate, and all those things. Okay, and from this properties, so from the definition, not the properties, from the definition, this is actually the definition of inner product. It should satisfy all these things. And from this, actually, you can find these properties. Just using the definition of the inner product, you can see these are the properties satisfied by inner product. Now that actually leads to one another definition, orthogonality and orthonormality. So we say two vectors u and v are called orthogonal if inner product uv is equal to 0. So just this is again one generalization of the concept of perpendicularity in R2. So in R2, you know, two vectors will be perpendicular if then this u dot v is equal to norm u norm v into cos theta, and there you can see that will be equal to 0. And similarly here, that is actually generalized to in a general setup, and two vectors are said to be orthogonal if their inner product is equal to 0. And from that itself you will get the, if that satisfies, if these vectors satisfy one more additional property, that their length is equal to 1. So by norm I have just meaning that the length of the vector, that's all. Okay, so if that, in addition to this, if in addition to the vectors being orthogonal, if their length is 1, then we can say that they are orthonormal. Okay, that is something which I have. So here you can see that inner product EJ, EK. If J and K are different, then they are orthogonal, then they should be 0. And if EJ, EK, J and K is equal, that is EJ, EJ, then what is should be? It should be 1. Okay. Norm, because EJ, EJ will be norm of EJ square. And what is norm of EJ? What is length of EJ? EJ is nothing but 1. So these are some of the examples. And now, so there is theorem. So every orthonormal list of vectors is linearly independent. So this is one theorem. This is again, you can see that. So if you have a orthonormal vectors e1, e2, etc., en, then you need to prove that it is linearly independent. Usually, how we proceed? Say c1, e1 plus etc. plus cn, en equal to 0, etc. plus cn, en equal to 0, and you have to prove that each C1, C2, etc. Cn is equal to 0. For that, you just have to take C1, E1 plus etc. plus Cn, En with itself. C1, E1 plus Cn, etc. etc. Cn, En. Okay, equal to 0. Sorry, not equal to 0. Just check this. What is this? And then you will get that all this C1, C2, etc. Cn should be equal to 0. So now again, once you get that a list of vectors are linearly independent, the question of basis will come, right? So which means this list of vectors can be extended to a basis of the vector space. And so since they are orthonormal vectors, I can say that basis I can call that a special name, orthonormal basis. So orthonormal basis is nothing but a basis of a vector space consisting orthonormal list of vectors. Okay. Now so what is very good thing about this orthonormality? Why we should talk about it? So in the vector spaces, usual vector spaces, you know, if you have a basis, you have just B is equal to, if you have a basis V1, V2, etc. Vn, C1, V1 plus VC2, V2, etc. plus Cn, Vn. That is how you write. But here, something more can actually talk about them also. So that is one good thing about here. See, in fact, actually, I know what are those scalars also. So that is, there exist scalars. These scalars are also being known when we have this orthonormal basis. So will you quickly go through that proof? Okay, this one. Why there exist scalars a1, a2, etc. an? Because we have our assumption is there exists an orthonormal basis, and then taking the inner product both sides of this equation with Ej gives inner product Vej is equal to, this is actually using the inner product property, because this actually reduces to inner product A1 E1 comma Ej, but A1 is a scalar, so I can write it as outside. So A1 E1 comma Ej plus etc. A2 inner product E1 comma Ej, like that. So which means what are they? They are orthonormal, which means they are orthogonal. So these will become 0. So what only remains is only inner product Ej will be non-zero, and this is 1. Hence, what remains? It is only Aj is what remains. Okay. So if we have an orthonormal basis, these are some of the things which we will get. And now, this is something, Gram-Schmidt procedure, which will guarantee you that, okay, there exists a orthonormal basis in an inner product space. Okay, I'm talking of all these things in an inner product space. Once I have started with the inner product, all this V which I am considering, all these V's which I am considering is inner product spaces. So inner product spaces is nothing but a vector space with an inner product defined on it. And inner product is what you have seen, that is a function. Okay, if that additional structure is also there, then we call that as an inner product space. Okay, I think I have skipped that, that's why. Okay, so now you already know that you have linearly independent. So suppose we have a linearly independent list of vectors in V, then you have a basis, right? So if you have a vector space, you have a basis. Now, Gram-Schmidt procedure actually guarantees you that you can get an orthonormal basis itself, an orthonormal list of vectors. So that is actually, you will get an orthonormal list of vectors. So here it is showing that if you have a linearly independent list of vectors, I can actually make them a orthonormal, I can construct, not make them actually, I can construct an orthonormal list of vectors from the given list of linearly independent vectors. And that is this procedure. So you don't have to worry much about these expressions. This is nothing but, so it is actually starting from a very simple step, say E1. So first you are already given a list of vectors. So I'll just take 2 more minutes. So you have already given a list of vectors, and E1, I just construct E1 from the given vector V1 in such a, so what we need an orthonormal list of vectors, right? So which means its length should be 1. So norm of E1 should be 1. So how can I make sure from a given matrix? I just divide it by length. So V1 divided by its length. So which will give you, so E1 is a, now E1 is a length 1 is a unit vector. Now E2. So E2 should be in such a way that it should be orthogonal with E1 and it should be length 1 also. So to make sure that is why I have written this E2 is equal to V2 minus inner product V2 E1 inner product V2 E1 into E1. So that is actually this removing the orthogonal apart from there and all those things. So this, the numerator part, we make sure to get an orthogonal vector, and the denominator part will make sure it normalizes, or the length will become 1. So that is this part. And one more important thing is the span of both will be same. That is actually the important thing. Okay, each stage, that is again one thing. So span of V1 will be span of E1, and span of V1 V2 will be equal to span of E1 E2. So at each stage, both the span will be same. So if you get time, you can just go through this Gram-Schmidt procedure, or you because tomorrow from the lecture, next lecture, he will be starting from here. I don't know whether he will explain this because he may not get time to explain all those things. Okay, so I hope now, I can conclude from here, the story to be continued. So what is the story to be continued? So now you have seen that I have a matrix, I have an linear map, I got a matrix, but when it is a operator on a complex vector space, I am actually getting an upper triangular matrix. Oh wow, very good. It's even better. And so V is an inner product space. I have more structure. I can talk about inner product, and I can talk about orthogonal vectors, orthonormal vectors, and in fact the Gram-Schmidt procedure will give you orthonormal list of vectors, and in fact that can be extended to a basis. Okay, now in these things, or now if this is the case, whether I can get the matrix in a better way. What do you mean by better way? Like now I have a very better thing, but now whether I can get only the elements in this. So what is our always aim is to work with very easy things, right, or nice things. So if it is a diagonal matrix, wow, it's very good even, but it may not be work with every cases. So in which cases you will get diagonal matrices, and in which cases you will get a little better. Okay, now if you are not getting diagonal matrices and you are already having upper triangular matrices, but whether we can get something in between, better than upper triangular matrix but not up to diagonal matrix. So that will lead you to the question of Jordan decomposition and all those things. So that is why I have written that the story to be continued. I hope like everybody says, stay tuned. The story is still there. So I have just given a trailer for the coming talks. I hope you understand, and now we can, I have just a few acknowledgements to make. Of course, thanks a lot to Sheldon Axler for such a wonderful book. Otherwise, I don't think I can I could have actually made it more simple rather than Axler has mentioned in his book. And then, thanks to Matoma College, actually it's my alma mater. So, in fact, I'm very much grateful for them for this opportunity. And of course, thank you for you all. No, last but not the least, but thank you for listening. If you have any queries, yeah, now we can discuss. Just a minute. I should.
Ma'am, could you please
Okay.
slide number?
Okay. Anybody asking?
Yes, ma'am. Could you please go for slide number 96?
Slide number 96.
Yes, ma'am.
Okay, just a minute.
That means you have proved that if each subspace UI is invariant under T, then we can decompose the space as a sum of UIs, right?
Just a minute. Okay, this one, right?
Sorry, ma'am, before that.
Here.
Ma'am, one more slide back, ma'am.
You can see. Okay, what will be? You just asked the question.
Okay, ma'am. Actually, you have said that if each UI is invariant under P, then we can decompose the whole space into sum of UIs, direct sum of UIs.
No, actually, the other way. We are actually assuming that U1, U2, the subspaces are U1, U2, U1 in such a way that V is equal to the direct sum of U1, U2, etc. U1. And then we are actually, see here, that is what? Let V is equal to U1. Can you see the slide now? So let V is equal to, I have started from this. Let V is equal to U1, direct sum, etc. U1, where each Uj is a proper subspace of V. And so, since working with a small vector space is AC, I am trying to look at T restricted to Uj. But one difficulty which arises there is T restricted to Uj may not map Uj into itself. So then I am actually considering only the decompositions where not like U1, U2 should be invariant, but I am taking in such a way that U1, U2, etc. UM are if they are invariant. If the direct sum, if you V is equal to U1, this one, and it is in such a, consider only decompositions of V of the form above where T maps Uj into itself. So the last sentence make it clear. Okay, is that fine?
Yes, ma'am. And then, ma'am, you have given equivalents for
Matrices
on to page, slide number 109.
Okay.
Is it only true for operators or any linear map? Because we have studied if T is a linear map from V to W, if the dimension of V and W are same, then the map is 1-1, if and only if on to, if and only if surjective. W may not be.
Why? Why? Because dimension of V is equal to dimension of W.
Yes, ma'am.
Yeah.
So, ma'am, the equivalence given in 109.
109. This one. Yeah.
Ma'am, is it only true for operators or any linear map from V to W where the dimension of V and W are same?
Yeah, but why? Because eigenvalue, where we will talk about eigenvalues. Eigenvalues, we are talking only on operators, right? Why? Because TV is equal to lambda V in such a way. So, this is for operators. So, that's why. When we are talking, this is where we are talking only about operators.
Okay.
Because, okay?
Okay. Thank you for that.
Okay.
Any more questions? Then let's wind up the session. We have come to the end of today's session. I'm sure this lecture helped the participants to excel in the subject. She has explained each topic very well with various examples. Thank you, Dr. Gayatri, for giving a better insight into the subject. On behalf of organizing committee and all the participants, I extend a heartfelt thanks to Dr. Gayatri.
Thank you, ma'am. Thank you.
Our sincere thanks to all participants. Tomorrow's session begins by 4 o'clock. See you all tomorrow. Thank you.
Thank you.
Thank you all. Thank you all.
Okay.
No.